Hello, and welcome to Sustainable Solutions, Reflections for the Next Generation. This is part 3 of our speaker series. I'm Dr. Jen DeRosa. I'm the Program Coordinator for Energy and Environmental Programs at Johns Hopkins University. And with each talk in this series, we've been hearing from innovators of sustainable solutions. These are practitioners that tackle real-world problems. As each part of the talk, they take us through the problem and how they've leveraged technology, policy, the private sector, and markets to form a pioneering and lasting solution. From water insecurity to climate adaptation to energy transition, this series provides a look at next generation applications in the field of sustainability. Now, you will have an opportunity to ask questions later on towards the end of today's talk. So when we get to that moment, please either use the Q&A at the bottom of your screen or the chat feature to post your questions. And my colleague, Dr. Hansen, or I will give voice to your questions later on. So today's talk is focused on energy storage, enabling the clean energy transition. Our presenter will be interviewed by Albert Cho. Albert Cho is the Chief Strategy and Digital Officer at Xylem, which is a global water technology provider dedicated to solving the world's water challenges. Previously, Al worked as a senior advisor to the Deputy Secretary at the US Department of State, where he was a White House Fellow and served on the Secretary of State's Planning Policy staff. He was an executive at Cisco Systems, a consultant at McKinsey & Company, and served at the United Nations. Al serves on the board of directors for the US Water Alliance and the Canadian Water Network, the program committee of Singapore International Water Week, and the editorial advisory board of World Water. Now, Al's talk was part 1 of our series, Solving Water in the Age of Climate Change. If you missed that talk, that can be found on the AAP YouTube channel, as well as part 2 of our series, which was How Energy Data Can Fight Climate Change, where Al interviews Kate Henningsworth from Arcadia. Our presenter today is Timothy Ash. Tim is the Director of Product Management for Fluence, a global leader in energy storage and digital applications for renewables and storage, and their headquarters is in Arlington, Virginia. Fluence delivers large-scale battery energy storage systems, software, and services, as well as software solutions to optimize the performance of energy storage and renewable generation for asset owners, electric utilities, transmission system operators, and large commercial and industrial companies. In his current role, Tim helps translate market, customer, and technology trends into the requirements and competitive strategy for the next generation of Fluence offerings. And with that, I'd like to welcome you both, Al and Tim, and thank you for being here today. And in the spirit of Zoom, if our virtual audience would like to offer a virtual welcome, please feel free to use the chat to do so and give a virtual round of applause in the chat. And also let us know where you're joining from, geographically speaking. And now I'll turn it over to Al.
Well, thanks so much, Jen. If you think back to why we're doing this series, it was really because with COVID, a lot of the in-person events to get exposed to different ideas have been harder to do. And so we came up with the idea of bringing in some speakers who could talk about the interesting work they're doing around sustainability. And so I told Jen and Cassie that I would go find who's doing some of the most interesting work in the areas of sustainability related innovation and technology. And that's we're now on week 3 or month 3 of that journey. As Jen mentioned, we started with water. Last month, we talked about cloud solutions for the power grid with Arcadia. And this month, we're going to zero in on one of the most important opportunities in sustainability, which is energy storage. So critical for integration of intermittent renewables, and therefore for the sustainability and the resilience of the power grid. And to talk about this, I'm just really excited to introduce you to my friend Tim, Tim Ash, who's the Director of Product Management at Fluence. Just for a bit of background, and just for students, how I ended up meeting Tim. We met as consultants at McKinsey about, I guess, well over a decade ago now. And while we were both working our tails off doing client projects, we somehow found time to become friends, and I've been really grateful for that because, as you'll see, Tim is just awesome. He has a heart of public service. He attended the Air Force Academy, served, and he continues to contribute to our country as part of the Service Academy Selection Advisory Committee for Eleanor Holmes Norton here in Washington, D.C. He's built a continuous career in sustainable energy, playing a wide range of roles that are all oriented toward accelerating the adoption of these storage technologies that are so important to the future of not just the power sector, but of climate change. And he's done all of that while being the partner of an amazing person who's also a friend of mine, and the parent to 5 great children here in Washington, D.C. And I don't know how somebody does all of those things, especially during the pandemic, and still finds time to share perspectives on energy storage, but here we are. This is why Tim Ash is so great. And so with that, I'm going to pass it over and ask Tim to talk a little bit about his journey and about what he does and why it matters. So over to you, Tim.
Al, thanks so much, and Jen as well. And good afternoon, good morning, good evening to everybody. I was watching some of the chats pop up, and I see everything from all parts of the US. I think I saw Dubai in there as well. And I understand from Jen that there's a global audience here as well. So very nice to meet you all. Hope to do this in person one day soon, but really appreciate the opportunity to chat with you. So what I'd like to do is step through a quick presentation here and kind of set the stage. So as Al said, kind of tell you a little bit about, what we're doing, why energy storage, why it matters, and then particularly, as the title says, how it's helping enable the clean energy transition. So that's me. As Al said, Director of Product Management. I've actually been in a sales role since I joined Fluence and our predecessor companies until a couple of months ago. So I was out trying to essentially convince people that it made sense to spend money on energy storage. I started in this business, I guess about 7 years ago now. And literally my first job was to go talk to utilities, talk to power plant owners. And we had this presentation and we said, all right, energy storage, for purposes of Fluence at least, is batteries in a box. And so here's a battery, here's a container. You should buy it. If you buy it, I promise you can make money, and we're gonna help make things better, make the grid more efficient, help decarbonize the grid. So I was having those discussions for years and years. As the industry has started to mature, actually was able to sell some of those projects, negotiate those contracts with customers. And through that process, learned a lot about what they cared about, right? So it's one thing to want to put energy storage in the grid to help make the transition. It's another to actually find a sustainable business model in which you can do that. And so taking those learnings now, and very excited to be coming into the role of product management, as Jen said, helping us think about what to do next. So that's me, or rather, that was me 4 years ago when the day we launched Fluence as a company. Better depiction of me on the right, so I'll let you take from that whatever lessons there are. So as I mentioned, so I'm with a company called Fluence. This is what we do. So the equipment in the foreground, all those white boxes, is a Fluence battery-based energy storage system, 50 megawatts, 200 megawatt hours, currently being installed and commissioned in California. So on the kind of rows of equipment you see going right to left are the inverters. The columns of boxes behind them are the batteries. And that's what we sell. So we put together these systems, we develop and deliver the controls, deliver them for our customers, and then provide long-term services and support to make them keep running. And then the software to help them optimize functionality in the grid. So help, again, with that transition. To give you a little sense of perspective, so each one of those boxes that you saw before, this is the ground level view. It's about an 8-foot by 8-foot cube. It's actually what we call it. Inside of each of those cubes is 743 kilowatt hours worth of batteries. So if you know the Tesla Model 3 baseline edition is about a 50 kilowatt hour battery in it. So that's 15 Tesla Model 3s per cube. And then, as you saw, a whole bunch of those stitched together to create an overall energy storage project. And why we're building them, or rather what those projects are doing, is essentially replacing these, right? So this is a snapshot of a peaking power plant. So there are peaker power plants all over in every electric power system. These are plants that run literally a handful of hours per year. You turn them on a very hot day or a very cold day for anybody in Texas, when the load on the electric power grid is at its maximum and you need a little more oomph to keep the lights on. They're very dirty. They're very inefficient, but they're built to be able to turn on very quickly, ramp up as needed, and turn them back off. So what we've been doing for the last 14 years or so is essentially trying to replace those. So the company I work for, the leadership for Fluence, has really been pioneering this industry. This is a picture of the first grid-connected lithium-ion battery system in the world in 2008. Each one of those two trailers you see is about a 1 megawatt system. You could turn it on at full power for about 10 to 15 minutes before it ran out of juice. But again, lithium-ion batteries, it's the same core technology that's in your laptop, is in your cell phone, and is now being put into your Teslas or other electric vehicles. So fast forward about 10 years, and we're about 10 times the size from a power rating. So this is a picture of an actual system we brought online at the end of 2020, beginning of 2021. This is a 100 megawatt project, so pushes literally 100 times as much power as those first two you saw. It actually has, if I did my math correctly, 1,600 times, I think, the energy. It's a 400 megawatt hour project versus a 0.25 megawatt hour project per container that we saw on the last page. So as you can see, the industry is moving very, very quickly. We've been helping drive and advance that. Again, Fluence, we're currently the leading integrator of battery-based energy storage systems like the one you see globally. We compete against companies like Tesla, Howin, but we currently are the leader. This is according to Guidehouse, I think put out this, this is an IHS chart that just came out. If you're familiar with NextEra, it's a big utility-owned company, or owns companies, including Florida Power and Light, is building their own projects. We also compete against the electric vehicle, car, and rocket company, and Wärtsilä is an internal combustion engine for boat company, but also very good at energy storage as well. But more importantly, why, right? So why are we doing what we're doing? And I love this chart. So if you may have seen this before, this is a plot of the correlation between the Human Development Index on the y-axis and electric consumption per capita on the x-axis. And so that yellow line cutting across the top, as you see, if you can read the label, is above that bar, you're at very high human development. Below that bar, you're not. So, but in short, what you see is electricity makes life better, right? It's a core part of improving the human condition for many reasons, like the cleanliness of air inside of your home, the ability to transmit work and do work very efficiently and cleanly. It's a core part of what we do and how we live. The problem, of course, is it's also a very significant contributor to global greenhouse gas emissions, right? So that dirty peaker I was showing to you and the many other generation assets we have in the world contribute to the bulk of greenhouse gas emissions, at least as of 2014 in this chart. So we all want to change that. So we want to get away from the fossils and go to what essentially becomes weather-based fuels. So now sunlight and wind ideally are the fuel source for the grid, as opposed to traditional fossil fuels like coal, like natural gas. But this creates some complications. So first, for full disclosure, some of the insights and some of the analogies I'll use next come from this blog called Honest Energy. I also wanted to share it with this group too, because if Adrian Yao put it together, if you go to this website, it's a really good first principles primer, very accessible to help you think about what exactly does it mean? What is the challenge that we're facing as you try to make this transition? So some of the images you'll see, I'm kind of pulling from that. I want to make sure to give credit where credit's due. So first, right, all the benefits we get from the electric power industry come from essentially the largest machine ever built. Right? So the AC alternating current electric power transmission, distribution, and generation system, right? So that interconnected web of the power plants, cables, transmission lines that bring electricity from where it's made to where you use it. And in an AC coupled energy storage system, in an oversimplification, right? So it's not actually a flow of electrons that transmits power, but it's the vibration, right? So again, using the analogy from honest energy. So the electrons in that grid essentially are vibrating back and forth at 60 hertz or 60 times per second here in the US, 50 hertz or 50 times per second in grids like in Europe. And so work produced at a power plant is transmitted essentially through those vibrations to the light bulb or your computer at your house. And as those vibrate back and forth, you have that frequency in the grid, right? So the way that the sine wave is going up and down. The way the grid is built, you have to keep that frequency as close to spot on as you can as the design frequency. So again, here in the US, that's 60 hertz, the nominal frequency, the nice green line here in the middle. You get frequency that goes too high, you trip things offline, you can damage equipment, you can hurt your computer, essentially the grid shuts down. Same thing when you go the other direction. And as you see, that you don't have to go very far, right? 1 or 2 hertz away from that nominal frequency. That is, you have to keep both the power on the generation side and the work being done on the load side in balance. And so say you come home and you flip on your lights, you're asking more work of the grid. There are large, spinning masses, essentially the generators from traditional gas or coal plants that are creating electric power. They're spinning, creating that 60 hertz frequency. I'm asking for a little bit more work on my end. That puts pressure essentially on the generator on the other side, and it starts to then slow down the rate at which it's spinning. So my frequency is going to start going down. The opposite direction is also true. I turn off the lights, or maybe I unplug my Tesla. The work I'm asking goes down. That same generator is still spinning. It feels a little bit less push. The frequency starts to go up. So we have to keep that in balance at all times, or again, the thing shuts down. This is Adrian's analogy. I really like it though. So if you then step back and think about, okay, what does that mean for us? This is the analogy he put together. On the left-hand side are all the various types of generation, right? So you see nuclear, diesel, solar, the turbines are that gas peaker that I was showing you. On the right-hand side, all the houses, the office buildings, those are the loads. That's the work that's being done. The wires in between are the transmission and distribution system. And then those people in the middle of this parade on the float are the grid operators. So they have to keep everything in balance. We need to all move forward together at exactly 60 miles per hour, not 61, not 59 miles per hour, or the whole parade kind of shuts down. So now the problem is, if we start taking out those tractors or the nuclear submarines there, I don't have the ability to control it anymore. Right, so if sun is my fuel, if wind is my fuel, I get power when the sun decides to shine, or the clouds aren't overhead, or when the wind is blowing. And when it's not, of course, then I still want to keep my lights on or my computer on. I start to run into some problems. Right, so this is a snapshot of the actual power from the solar panel, comparing the red, nice, predictable curve on a typical sunny day. But on a partially cloudy day, you can see the amount of work, the amount of power that solar panel is going to put out varies tremendously, right? And so I'm not changing anything on my end. I want to keep using as much power. Now there's not as much available on the other side. Now I'm having a real problem with that balancing. So this is really an example kind of, within the hour, even within the minute, that balancing is going on all the time in the grid. This also happens over the course of the day and even seasonally, right? So if anyone out there is familiar with the infamous duck curve in California, what this chart is showing essentially is the net load on the California transmission system, right? So the curve is how much load, how much demand coming from all those houses, those business parks, your Teslas plugged into the grid, is the grid seeing, and those transmission operators, the people on the float, need to tell all generation to be ready for. And what's happening, the reason you see that curve keep pushing down and down and down year over year, is that they keep installing solar, right? So if you flip that curve over, that's actually a solar generation curve. That is, now I'm putting in a whole bunch of additional energy from other places in California, particularly on rooftops, such that now the system doesn't need to push as much work. I don't need as much out of the diesels, the nuclear subs on the front end of my parade. The problem is now over the course of the day, as soon as the sun goes down in the evening, everyone's coming home, I'm turning on the television, I'm starting to cook dinner, the load still goes back up to where it used to be. And in fact, it continues to grow. And because I no longer have my solar panels, maybe I have my wind, maybe I don't, I need to turn something else on to maintain balance and keep that grid up and running. Now I'm still stuck with those same peakers unless I find some other alternative, right? So enter energy storage. So back to that parade analogy, what energy storage does now in this new grid, right, we have much more variable, generation, the trucks pulling everything, trying to keep it 60 miles per hour. Maybe those are going 70 miles an hour, maybe they're going 10 because there's a cloud coming overhead. So that's kind of moving back and forth. Same thing's happening on the backside now on the load. I've got solar panels on the roof. And so maybe now I need a little more, maybe I need less, maybe I'm actually starting to pull forward the ramp as well. So you can think of grid storage essentially as a spring in this case, right? It's creating the slack. So it's soaking up some of that extra energy coming from the generators when it's there. And now I can push it back in to support additional load when it's not. So that's really the core problem that energy storage is solving, is maintaining that balance in the grid between work that's being asked and work that's being created. As you shift then, so let's think about moving to 100% renewable electric power grids. The good news is this is starting to look more and more feasible. I grabbed a couple of quotes here from the National Renewable Energy Laboratory here in the US. You see on that top one, highlighted in yellow, growing confidence that we can actually maintain a reliable grid, keep it in balance, even with a 100% renewable generation fleet. And key to that, of course, as we just described, is energy storage, right? So there's some big role that energy storage will play in that transition, for sure. And at each of those different levels, right? So again, back to that picture of the variability in solar as the cloud goes over, the minute to minute kind of variability, short-term variability on the bottom. We've honestly largely solved that. Right now, lithium-ion battery-based energy storage is economic. It's cheaper to build a battery peaker plant than it is a new gas peaker plant. The reason my company exists is because we've largely gotten there. The diurnal problem, so talking about that duck curve in California, so shifting big chunks of solar or wind energy when it's being created to the time when we need it, we're getting there. Very interestingly, lithium-ion batteries actually just won a big procurement here in the US and California to deliver an 8-hour solution as well. So you're starting to get into a pretty significant portion of the day. There are longer term problems though, like shifting energy from summer to winter, or covering an entire week maybe when you've got a big storm coming through Texas or Ireland or somewhere else. And so that's going to take a little bit more work, but clearly energy storage is going to be a significant portion of the solution. And so putting a kind of business perspective on it for a second, this is a snapshot from Bloomberg New Energy Finance, looking at cumulative energy storage installations, over the next 8 years or so through 2030. 350 gigawatts, right? So that's 350,000 megawatts, that first project I showed you, the building-based project, is 100 megawatts, to put that in scale. Or depending on where prices go, something on the order of a couple $100 billion per year industry just for energy storage, largely in that short-term kind of diurnal space. Even more interesting, so for those who are out there and interested in getting in the space, there is a lot of work that's going to be required. IEA put out a report called Net Zero by 2050 here a few months ago. In it, they estimate that we need to invest around $4 trillion per year, starting by 2030, to get to a net zero power economy, right? So not just electric power, but electrifying transportation or decarbonizing transportation and other sectors as well. So to put that in a little bit of context, the entire global GDP, or the largest global gross domestic product ever, was 87.5 trillion in 2019, just before the COVID pandemic, and where it's come down a little bit. So there's a lot of work to be done. Energy storage will play a very significant role, but clearly there's many other elements and many other pieces that we need to put together. So I'll stop there. Again, thank you very much for the opportunity to kind of tell the story. Hopefully that was somewhat interesting, give you a little bit of a snapshot of why energy storage, the role we're playing in the transition to a clean energy economy, and why it's a really fun space to be in, both from a personal, but also a business perspective. So thank you very much.
Thank you, Tim. I want to remind our audience that they can ask questions using the Q&A button, but also the chat as well. Either location is fine. And Dr. Hansen and I will give voice to your questions. I do have one question to start us off. And this is really kind of about how you got to where you are. So you had such an interesting career from before Fluence, starting with the Air Force to McKinsey and onward from there. How did you end up doing what you do, and have your prior experiences helped you to succeed, to get to where you are?
Yeah, it's a good question. It's it's fun when I sit where I am now. I can tell this nice story about a linear path from starting in the Air Force and through McKinsey, as you just described, Jen, and into this role. The experience, though, when you're moving forward, and it can feel somewhat random. So, for me, as Al mentioned, I was really passionate about public service, both from my education. I have a public policy degree from Harvard Kennedy School, served in the Air Force as an intelligence officer. And when I got out in 2007, I was really interested in this question of, how do we solve these really complicated problems, right? Multifaceted problems, things like clean energy transition. I grew up in a small farm town. And so the original idea was like, hey, like biofuels was kind of kicking around at the time, 2007, 2008 timeframe. My wife was working in international development at the time. And so I thought, hey, what if I can work on that problem, right? So use, otherwise not very useful land, plant things like jatropha, turn it into green fuels as a drop-in replacement to help green the economy. So that sounded great. I had no business experience. I didn't know anything about energy. At that point, I had a mortgage and my first child on the way. So went to McKinsey and Company essentially as a way, management consulting firm, as a way to kind of get a real world MBA. So understand how to think, from a business perspective, some problem solving, and try to get some exposure to, the energy and clean tech industries. Very lucky to be able to do that. Worked on a solar project that really cemented it for me. I was like, I love this space. Like I was reading a 350-page engineering book about the manufacturing process of PV silicon solar panels, and I loved it. And then honestly, just kind of good luck from there. So I knew that became my kind of North Star professionally. Had the chance to jump into a small startup here in DC, took a little risk trying to bring a new technology, new electric power. That failed spectacularly after about a year. And then, but I knew I wanted to do it, found an opportunity. It was then AES Energy Storage, which then transitioned into Fluence. So, it was, I guess, trying to learn about my passions. And when I found them, trying to find a next step that would take me, one more closer, because I certainly started a long ways away from where I am today.
Thanks for sharing your journey. I think a lot of us can kind of relate in terms of following your passion, but it also being somewhat of a windy road along the way. Thank you.
Excellent. Well, so I have questions that are rolling in. So I'm going to bundle two together here and ask the first question. So the presentation had wonderful visuals, the spring example with the kind of the give and get, push, pull, create and use. So the first question is about energy storage as it relates to latitude, and how that's going to change for renewable, places. Higher latitude gets at certain times of the year less solar radiation. Could you talk a little bit about the additional needs for storage for places at different latitude, and then perhaps reflect on the demand of energy storage for the U.S. from a regional standpoint?
Sure. So yeah, latitude. This is an interesting question. I mean, energy storage really, so even if you weren't worried about a transition to renewables, energy storage actually benefits the grid significantly just in playing that balancing role. Just starting from, let's replace those dirty peakers with a battery instead. So even if you're still using fossil generation, it allows you to significantly or materially reduce emissions just by allowing more efficient baseload or intermediate generation to run more frequently. So energy storage has a benefit to a grid anywhere, regardless of latitude. And so then I think the question then goes to what's the mix? You're going to see a different mix of renewables depending on where you are. So Brazil, for example, relies very heavily on hydro and a lot of biomass as well. You can argue how renewable biomass is. Southern California, desert Southwest here in the US, Israel, Middle East, you've got a tremendous amount of solar capability. Further north or central US, a lot of wind. Ireland, UK, a lot of wind. And so I think what you see is that the mix in the grid will vary. Therefore, the kind of impact and the specific problem you're solving will vary. But the great thing about storage is it kind of comes in any shape or size, right? It can be 1 megawatt, 100 megawatts, 1,000 megawatts, and then you can extend how long, how much energy you have behind that. Can it run for an hour, 2 hours, 3 hours? So people describe it variously as the Swiss Army knife of the electric power grid, or bacon of the electric power grid. I've heard that too. But so you can kind of help solve that problem regardless of the specific shape of the grid. And to the question on the US, for energy storage, at least, really the driving force has been California. The underlying economics, for all the reasons we talked about, makes sense. It's the lowest cost way to deliver power now. Is solar and wind are the cheapest form of new energy. Energy storage is the cheapest way to create the flexibility need to absorb it. So it's making the grid better for California, and California decided to create a mandate. And so they've required all the utilities to buy, I don't know what the target is now, 15, 20 gigawatts. I'm sure I'm getting the number wrong, of energy storage. And so that signal created a very definite market. So for companies like us, we're like, okay, we've known the economics make sense for a long time. It's hard to sell it because the regulatory market structures aren't there. But California said you have to. So I know that someone can buy it because we know it makes sense, and now we can go sell. So California is driving it. It's about as big as, it's about a third of 25% of the total global market from our perspective. Desert Southwest, Arizona as well. But you're seeing it all over. I mean, Connecticut has a mandate now. New York, as they drive towards renewables, even in the Southeast with companies like Southern Power are starting to see benefits of energy storage as the economics and the performance continue to improve.
So the client currently is the states that are looking to expand their energy efficiency and holding.
Yeah, well, they're driving it at least. Well, for us, and to be clear, I think as Jen said in the introductions, we serve a lot of different types of customers. The conversation I kind of stepped you through today is really focused on the electric power grid. And so our customers are actually the companies who own power plants and then sell that energy into a grid like California ISO, or Air Grid in Ireland. And so depending on the market structure, so we're not necessarily selling to the utilities. The utilities do buy some, but the states, excuse me, the states are really creating the market structures and the mandates to help support the transition.
Excellent, thank you. The picture that you showed of the 8x8 block was wonderful, and a question that actually popped into my mind, and someone, one of our audience members asked as well, was could you speak to some of the challenges that you face with the supply chain issues that have cropped up over the last couple of years regarding the production of battery storage?
Oh yeah. I mean, so two things. Well, maybe it's one thing, right? I mean, we're being hit by the disruption to supply chains, like just about every other industry. I was listening to the news the other night, and they framed it well, where as the COVID pandemic hit, we essentially transitioned or traded services for goods, right? We can't go out anymore. I can't go to the movie, so I'm going to buy something instead. I'm going to buy like a new air fryer and make my dinner at home. And so the pattern of consumption changed dramatically. I think I've heard 40% or something increase in imports from Asia. At the same time, the whole supply chain got disrupted, right? And so both we need to move more stuff, and we had less ability to move it. Most of the lithium-ion manufacturing capacity in the world right now is in Asia, in Korea and China in particular. That's where we get a lot of our batteries currently. So that had huge impacts for us. I mean, the cost to ship those batteries went up, I think it was fivefold just to transport them. And now you're seeing the same thing kind of ripple through commodities. Is I guess the other piece of it is, again, as that consumption increased, and for us specifically electric vehicles, we're using the same batteries that electric vehicles are. That demand all of a sudden has outstripped supply, and so you're in a commodity cycle. So prices have been going up to move them, prices have been going up to make them. We're certainly being impacted by that. We have a lot of mitigations in place, and there's a lot of business positions we've taken to help mitigate the impact for our customers. But it's certainly something we're wrestling with. In my personal view, again, it's a commodity cycle. 18 to 24 months, I would expect that sorts itself out. Specifically, is it 18? Is it 24? Is it 36? We'll wait to see. But yeah, it's certainly a challenge for us as well.
Thank you for explaining the situation, Tim, with regards to supply and demand. I have a question with regards to that. And one is relating to kind of where's the battery technology kind of heading towards in the future, and if you could sort of look into your crystal ball where you think it's headed. And then with that in mind, do you think we're going to get to a point where the US will be able to source its own batteries domestically instead of relying so heavily on foreign imports?
Yeah, so I should caveat all that by saying I'm not a technologist, right? So I come at this more from the commercial business kind of strategy perspective. That said, in the near term, for like the work that we're doing, again, so trying to create a commercial business around energy storage deployments, in particular in the grid. Lithium-Ion it's so big and it's so mature right now. It's really going to be hard to beat, and you see that. I think I mentioned California's had a big push towards longer duration energy storage, and so 8-hour minimum. Most lithium-ion energy storage applications tend to be kind of 1 hour duration, 2 to 4, depending on what market you're in. So hitting that kind of narrow peak, the head of the duck in California. As we said, there's absolutely a need for longer durations as well. So the first procurement in California came out asking for 8-hour energy storage systems, and lithium-ion won. It was not only the winner, it was the top 10 on that list versus some of the other innovative technologies that are out there, like flow batteries or and various other longer duration technologies. So I think in the near term, the economics of lithium-ion and the performance is just really hard to beat. There's, literally billions and billions of dollars in manufacturing capacity and investment and R&D going into that technology. So you'll see a lot of evolution in that space, right? So lithium-ion batteries every year get better. You start moving towards solid lithium metal. And so instead of having an aqueous electrolyte, you have no electrolytes. So some of the issues that have come up with lithium-ion batteries around heat and degradation and safety are solved. You get much better density. So within that space, things are going to get a lot better. And then you look at other competing technologies. Green hydrogen is kind of having a moment again. So can you use all of that excess solar and wind to create green hydrogen? So split water, create green hydrogen, and then that becomes your energy storage for that seasonal problem, or where it's hard to use a battery, drop-in fuels for trucks or airplanes, things like that. So there's a lot out there. And again, and not to say that the flow batteries and the other technologies that are out there now won't continue to get better too, but they have, again, those are small companies competing against global behemoths at this point. And to the US, yeah, absolutely. There's a lot of investment already happening in the US, again, primarily driven by electric vehicles. SK is just building a plant in Alabama here in the US. I believe there's some new capacity coming in Canada, not the US obviously, but North America, up in Canada, and around the vehicle clusters here in the US and Detroit as well. So it's definitely coming. You're also seeing very significant investment in Europe. So everybody sees the opportunity, or the need, I should say, and it's coming.
Thank you. That's exciting to hear.
I'm going to wrap up. I'm going to put two questions in one here. We have so many questions that are pouring in. So can we get your perspective on how climate is impacting storage, and from the standpoint of, is temperature a huge factor here in the role of efficiency? And then in places where you have these large arrays, with wildfire smoke causing cloudy conditions for periods of times, sandstorms, ice storms, extreme temperatures, how are you finding that that's impacting the ability to store energy?
I guess the short answer is it doesn't, or at least that's one of the strengths of battery-based storage versus, right? Because if you look at energy storage as a category, by far the most energy storage we have is actually pumped hydro. I think it's north of like 23 gigawatts of pumped hydro capacity just here in the US. So if people aren't familiar, essentially you have a reservoir at the top of a mountain, pump water up when you have excess power. So that's you soak up the extra energy in the pump, and then you use gravity to spin the same turbine on the way back down when you release it when you need a little bit more. That was built out here in the US, at least largely to support the nuclear power fleet, built out in the 1950s and 60s, because they're really hard to turn off. And so if you don't need that power, you got to put it somewhere. So that's actually the biggest energy storage capability out there. It's also really hard to build now because it has a huge environmental impact. It's geographically specific. You have to have that elevation. You have to be able to get permit. There's water issues now, as I think you talked about a few sessions ago. So it becomes challenging. So the great thing about battery energy storage is it's 100% independent from the environment it's in, essentially. So the issues that folks are raising will certainly impact the generation, whether it's solar or wind, right? So that's introducing issues into the grid. But we're building a system it's a 20-year asset. It's built to be very rugged in an outdoor environment. They're air conditioned, they're safety systems. And so the impact of the storage systems that we build is, it's not huge. It's an engineering problem that we've solved for many other technologies.
Is there any discussion of future expansion into microgrids from your side?
For Fluence, well, so again, we're looking really across different applications. So the great thing about energy storage is there's lots of different types of problems that you can solve. Again, we talked about the electric power grid itself, but if you think about, for a commercial industrial company, for example, you can help reduce the cost of their generation, right? So when they're turning on a steel plant, for example, they've got a big load, maybe costs them a lot of money. I can kind of lessen the impact for them. So there's some commercial applications for energy storage. And then as the question is asking about within microgrids, right? So as you move to create smaller and smaller grids, where you have the ability, if the large grid goes down, now I can keep the hospital up and running, or the school, or the police station. And so how do we create a little grid with our own generation, whether it's solar, and put batteries in, and it serves that same function, right? So it's that same balancing stability function in the microgrid or in the macro grid. So short answer is yes. I mean, we're certainly looking at that. We're in a leading position now. We very much want to remain in that position and continue to bring the benefits of the technology to many different applications.
All right, thank you so much. Again, all these questions are really great. So I'm like, okay, can I combine multiple questions together here to ask one mega question? Let's see. So the one that I was going to pull on here is for future involvement with resources. Perhaps, I know you mentioned the value of lithium, but is there any type of exploration and new approaches that you foresee out there on the horizon that could be a maybe cost-effective approach from a sustainable side of things?
Yeah, sure. So well, I've mentioned a few of them, right? So hydrogen, like green hydrogen, it's a different way to store energy or convert, wind and solar into a different form of usable chemical energy. That's a big one. I mentioned the flow battery technologies, and so lithium-ion batteries are, as you know, like it's a cell, it's a closed system. Flow batteries essentially use liquid electrolyte in two tanks, and they pump them back and forth through a membrane, which does the charging and discharging. So it's a different type of technology. So vanadium, a lot of the technologies out there are based on vanadium. It has some, there's some benefits that people tout about it, but that's one that's out there. More immediate that I've started to see is sodium-ion batteries. So it's a very similar structure, similar chemical process to lithium-ion, but using sodium instead. There's some trade-offs in the performance of that, but that appears to be, it's being commercialized now and seeing it come out as well. But then, I have companies like, I'm gonna get the name wrong, ESS, they have a rust battery effectively. So there are a whole bunch of different technologies that are out there that are theoretically feasible. The real challenge is in how do you get them to a commercial maturity where you can get to a competitive cost point. You have banks will give you a loan because they trust the technology. Do you have a supply chain there? Do you have people who can maintain it, that can fix the system, right? So yes, there are a lot of interesting technologies. Generally, the much bigger challenge in clean tech is how do you commercialize it and make it an actual sustainable business.
Thank you. One question here, wanted to know how you perceive the vehicle to grid solutions for EVSs as they continue to roll out. How does that play into your company's goals and workflows?
Yeah, it's a great question. So the idea, if people aren't familiar, is, with all the electric vehicles that are out there, Ford here in the US actually has a commercial now that shows this. But the idea is, you plug your car into the grid to charge it, but now it's a battery full of energy. And so if the grid needs it back, you just push it back out of the car into the grid. And so instead of building systems like ours, now you have 20 million electric vehicles plugged in. It's a ton of battery capacity. As I mentioned, I saw a commercial from Ford where I think a F-150 pickup truck rolls up to the house that's dark, and they plug in the car, and then the lights in the house come on. It's interesting. Actually, the origin story for what was AS Energy Storage, now Fluence, actually came from that question. The PJM interconnection here in the US, it's the largest interconnection grid, I believe, in the world. Connects most of the Midwest, Pennsylvania, New Jersey, out through kind of Chicago. They were looking at vehicle to grid. So how could they test plugging, a megawatt or 2 megawatts worth of cars into the grid and figure out what the impact was in maintaining that balance? Our leadership at the time said, well, how about we just put all those batteries in the container instead? And that was the picture that you saw. So the original kind of spark for our company actually came from thinking about that problem. So I personally, I'm not in that space. So I think the challenges there are you can't control when it's there, right? People need their car to go to the grocery store, they unplug it. And so from a grid operator perspective, it's less predictable. It also becomes an interesting challenge. You're like, hey, okay, I've signed up for that program with my local utility. They needed the energy and they pulled it out at 7 in the morning. Now it's 8:30 and I got to get to work and I've only got 10% charge in my battery. So you need to solve for some of those problems. It also, batteries wear out, right? So all of with your cell phones, I'm sure over time lithium-ion batteries degrade, you get a little less energy out of them. So who's paying for that extra wear and tear? So it's a great idea. Again, it's this tremendous resource that's there. Computing power, distributed, computing is helping us create the systems to try to control a mass network like that, but it's a very complicated problem to solve.
Okay, so another question that we have coming in here is regarding codes such as the UL, IBC, IFC, and the NFPA to help clarify relevant codes. What kind of approach does your company use to help streamline this project as it pertains to permitting process for projects that are under development?
Sure, I was getting very specific. So that's referencing, so UL, Underwriters Laboratory here in the US, you see the stamp on the side. So it's essentially this, safety standards. All different products have them, from your toaster to your cell phone. And then there are different standards. I think it's IE in Europe and other locations. NFPA is the US National Fire Protection Agency regulations here in the US as well. So I think the point of the question is there's a tremendous amount of compliance requirements that come in, and a company like ours, which is global, they also then vary from country to country and market to market as well. So I guess the answer is, that's a core part of our business, a core part of what we do is we design our systems. We design them to make those meet and exceed those standards, to be honest, do the testing and to get the certification to be able to offer into the market. It's kind of table stakes to be in the game. They're also evolving very rapidly. So as the technology grows and matures, the UL testing, for example, around fire safety for lithium-ion batteries, moving from, it was Rev 3 a couple of years ago, now we're in Rev 4, and that standard changed. These are kind of 2-year, 3-year project timelines as well. And so we need to be a step or two ahead of that. So I guess the short answer is it's something we have to pay attention to and do. And as a company, we really try to exceed the standard as well, right? Because safety is really our first priority as a company.
We had a question on, could you mention the name again of the electric system network in Pennsylvania and the Midwest that you mentioned earlier that was the largest in the country?
Yeah, it's called the PJM interconnection.
Okay, thank you.
I think it was Pennsylvania, New Jersey is the J, Maryland. I think that's where the name comes from. I'm going to get in trouble for not knowing that off the top of my head, but yeah, PJM.
Okay, thank you for that.
There's a question about, could you provide some thoughts on the Lithium Valley project that's being proposed? Any thoughts regarding this particular project?
The which projects?
Lithium Valley, I believe it's in California.
I don't know that one specifically.
Okay, we can come back to that. Maybe the audience member who posed the question can expand upon that question.
My apologies. There are many, many projects in California, as I mentioned. It's really a big driver in the industry.
Yeah. Thank you. I guess the next question for our students, the folks that are in the environmental sector, the renewable energy sectors, what advice do you have for the students to make sure that they're staying tuned in and they want to be on the edge of cutting edge technology? That's why they're here, and they're listening to the experts in the field. What advice do you have for the next generation of our students, our stewards?
I mean, I don't know that I have any real unique insight there other than, doing what you're doing now, right? Which is one, finding like-minded communities, right? So I presume the group on this call, both your students and maybe others who are participating, there's lots of different platforms for that. I know there's, a few young professionals in clean tech, for example, organizations that have sprung up here in the Washington, D.C. area that I'm aware of. My colleagues on the West Coast, I know San Francisco is kind of a hotbed for that as well. But again, across the country, I mean, Iowa is one of the biggest leaders in the country as far as renewable power and wind. Texas, actually, I think is the largest, both for solar and for wind. So, so one is finding that community, and they're everywhere. I think, again, probably the obvious, like, get plugged into the various news sources that are good. Canary Media is one that a lot of people follow. Came out of what was Green Tech Media when that kind of shut down. So Canary is a really good one. I don't personally use Twitter, but the Energy Twitter, #Energy Twitter, I'm told is actually a fantastic forum. There's a lot of great conversations and threads. That, again, the Honest Energy blog that I flashed up before, someone in my company ran across it. We have no connection with them whatsoever, but it's a really great resource. It's a really great primer. And so there's a lot of different ways to get plugged in, stay close to it. And, if my meandering path to get to where I am now is is of any use, just keep trying to find, that next step that gets you a little bit closer. Sometimes it feels like you're moving a little bit sideways, but maybe it's, taking the job. It's not the job you want, but it's the company that you want, or it's in the space that you want, right? Or it is the position you're interested in, but not in the company yet, right? And so you can kind of keep making those moves as you go, and keep your ears to the ground, because there's the luck element, which you can't control, right? So just try to stay as close as you can, so you can see the opportunities and be as best prepared for when hopefully you have the good luck to encounter them.
We have one more question I'll pose here.
Okay, I was going to have you ask one more question, and then we can wrap up. Thanks.
Okay, excellent. So outside of the U.S., I know you had a couple of charts that showed different countries, excluding China. What is the next country that's showing potential for battery storage potential? Yeah,
well, and it's beyond potential, right? I mean, there's the energy storage is a global industry now, and the opportunities there. So, the bigger markets, if you just look at number of projects being deployed, Australia, UK, Ireland, India is really starting to take off. So it really is global already. Israel's had a big push recently. So the kind of relative size of each of those countries is changing, but it's already there. Again, I didn't show the picture, but the first commercial project that we worked on as a company at AES was built in 2008 in Chile in the Atacama Desert. And so, it's been economic there, for 10, 14, how many years ago that was now. So it's global
already. Thank you. I want to first, before we do a final wrap up, I wanted to thank you, Tim, for talking today about energy storage and the energy transition. I think that's a really interesting topic for our audience. And judging by the volume of questions and the number of people that joined today, I can tell that there's a lot of interest in this area. I also want to thank Al Cho for helping to organize this entire series for us this year, and really helping connect us with a lot of these sustainability solution innovators. And then also I want to give a shout out to Peter Huggins, our events manager at JHU AAP, who none of this would be possible if he wasn't plugging us all into a Zoom webinar and allowing us to meet with you. And then also I want to welcome Alexandra Shiri, who is our newest social media manager here at JHU, who's also helping to get the word out to you on social media when we're having these wonderful events. So thank you for joining us, and feel free to give us virtual applause or to Tim and Al in the chat. And our next event, I believe, is scheduled for March 3rd. Does that sound about right, Cassie? Okay, March 3rd. And look for more advertisements and heads up coming on social media, email, and all the normal channels that we usually push out to. So thank you.
Thanks so much, everyone.